Hi, it's Robin. Some time ago, I made a video about a Commodore PET game called Manbiki Shounen, which translates to Shoplifting Boy. It was made in Japan way back in 1979, which already made it interesting, but there were at least a couple other interesting details. For me, many game historians consider it to possibly be the first stealth video game ever, and it was considered lost, as in the people looking for it couldn't find a copy to play. Then I got a tip from Ryan Devan that the game had been located. It had actually been published in a Japanese computer magazine called RAM, Random Access Magazine, as a type-in program listing in the February 1980 issue, and scans of the magazine were available on a Japanese language webpage. So I grabbed these and tried the game out, and thought the game was actually pretty fun, if a bit sluggish. So I started examining the code to see if I could optimize it. My goal was to minimize changes and preserve as much of the code as possible to keep it pure basic so it could still be a basic type-in like in the original magazine. I also wanted to make it still work or run in a PET with just 8K of RAM, which was quite standard in 1979, 1980. Now, the original game only leaves about 225 bytes free, so it really can't get much bigger. In the previous video about this game, I want to keep the focus on the original game from 1979, and I made sure the original unmodified game is preserved as the first game on the disc I released, which is available for download in the video description. Now, in this video, I want to take a look at the optimizations I made to make the gameplay of Manbiki Shounen faster or more smooth. You might find some of these ideas useful in your own programs, even if it's not for the PET, as most of the ideas will apply to other Commodore computers and maybe even other platforms. Now, a lot of the code in the game is devoted to things other than gameplay, such as the title screen, game intro screen, the 2 game over animations, which are played depending on whether you lose or win. This is actually an incredibly animated and polished game for 1979, especially for a magazine type-in program. Optimizing all those animations isn't necessary, so I didn't touch them. It's actually only about 20% of the code that is the core gameplay, and that's mainly what we're going to be looking at today. So I've got a special version of the optimized game loaded up here on my Tynemouth Mini PET 4080 from The Future Was 8-Bit, and we're going to walk through the changes line by line. The original program didn't have any rem statements, that is, remark or comments. Those are a luxury they couldn't afford with 8K of RAM. Just for the purposes of this code walkthrough, I've added some rem statements and actually bloated the program up beyond 8K, so it needs at least a 16K PET to load this special explanatory version. The mini PET here actually has 32K, so we've got loads of RAM. And to be clear, the optimized version on the disk image for download still fits in 8K. It's just this version that we're looking at today that is bigger, just to help with explaining and comparing what I did from the original to the optimized version. If you see a remark in the listing, you'll know I added that just to help explain. So that's what line 5 here is, just a remark from me that I added line 10. So for whatever reason, the original program did not start with a line 10. Start at line 20. I've added in this dimension statement, and all this is doing is pre-initializing a whole bunch of variables, reserving space for them in memory. You might know that BASIC creates variables on the fly, dynamically allocating space for them, and every time you refer to a variable, it first sequentially checks through the list of already initialized variables to see if it's already defined, and if not, then it creates a new one at the end of the list. So as more and more variables get added, that search process takes longer, and variables near the beginning of the list, that is, those that are defined first, actually are found substantially faster. It can make quite a difference in the runtime. These variables are defined in the order of frequency of use. This variable A is used more than any other, so we've dimensioned it first. That's the Warden's horizontal position. iString is the variable that checks for a key press. X and Y are the shoplifter's X and Y position, and so on. Now, you could just make an educated guess at defining this order, but you may have seen a previous video of mine called Faster 64 that's actually a profiler for the Commodore 64 that will count every variable use, and then at the end of the program run, it will produce a list of variable names in the order they were used. I actually used that Commodore 64 program to analyze this PET game. After we're done this PET code walkthrough, I'll switch to the C64 briefly and show you how I came up with this list of variables. So we'll just be looking at the code in chunks. I planned it out ahead of time, just trying to make sure enough of it fits on the screen at once. Now, if you look at this, you'll probably notice an oddity here at line 2030. There are two line 2030s here and here. The first one is commented out with a rem, so for the rest of this time, whenever you see a pair of lines, the first one should be commented out. That was the original line from the game, and following it is a second line that I've replaced it with. In most cases, this is the optimized version of the same line of code. Once in a while, that wasn't possible because of the way what the changes required. In this case, you can see that the beginning of the line is the same up to this point, s equals 0, and I've added on some extra commands at the end. So again, the final game that you might play doesn't include these duplicated lines. This is only for demonstration here. While I was trying to make this video, I kept sidetracking myself with these sort of things. So for this video, I'm going to ignore how I made these duplicated lines. You might know that this isn't normally valid basic. If you type in a line of code with an existing line number, then it just replaces the old line with the new one. So there's some trickery needed to do this. I think I will explain that in another video, but I will explain why I did this. I thought it would be good to be able to see both the old and new line of code on the same screen. I was trying to solve a problem here. I don't have a dual screen PET. It would have been a huge pain to try and record two separate PETs at the same time. I don't know. I couldn't do that. Or to do one and then the other and then try to edit them together and make it clean. It would be a big mess. So anyway, this is my solution, how to show you the original and the new one, is to make an invalid program like this. I suppose I could have just used a different line number, but there's two reasons I didn't want to do that. There's a couple times in this listing where there actually wasn't a spare line number. The line numbers were already all taken. I wasn't about to renumber it because I want to keep it the same as the original as much as possible. And I wanted to make it absolutely clear which was the original and which was the new. Some of the lines are so different, you wouldn't really know if it's a replacement or not. Oh, that just seemed ugly. I thought this was kind of fun anyway. Anything to distract myself. And one other thing here is that if you do have these kind of duplicate lines, you can't actually edit the second line. If I was to go in and start typing over this, and I want to make some changes, I press return. I won't do that now. I don't want to mess it up. But if I did go in here and make some changes and press return, it wouldn't actually edit this second line 2030. Commodore Basic would search through from the beginning to the end and find this first occurrence of 2030 and replace it with that. So effectively, we would be erasing or losing the first line, and the second line would be there. You'd actually have to delete line 2030 once by typing 2030, return. Then you could edit the remaining line and it would replace it. Okay, finally to talk about the actual edits. Sorry about so much preamble today. Okay, so the original sets the time clock to, this is 3 minutes past midnight, but this game uses a scale of real-time minutes to reflect in-game hours. So it's actually setting it to probably 3 p.m. So that I kept the same. S equals 0, that's initializing the score to 0. This is just a brand new game. But I had to add these lines. What I really wanted to do was just go to 3080. Well, actually, I didn't even want to do that. I had to. We'll look at it in more detail later, but what I did is I made it so that the player, the shoplifter, only gets redrawn if he moves as an optimization. And that eliminated all the flickering that the original game did. Even if you're just standing still, the player was flickering because it was being erased and redrawn in the same spot. So I optimized that so it looks a lot nicer. The downside is that the logic to redraw only does trigger if you've moved. So after I completed those optimizations, I ran the game and the player didn't appear at all when you start a game. He's like invisible or not there. And then if you move blindly, then he appears. So that was a bug. So my solution for that was to just jump straight into the code that draws the player on this initial loop into the game. Here we are, we're just setting up a new game, and we're going to jump ahead into the player draw code directly, and then the game loop would start happening. Yes, for a single iteration, the shopkeeper, I think, doesn't appear, or the score doesn't appear. That's not a big deal. It's not nearly as bad as just having the player not there at all. Okay, and because I had to do that, I then learned I had to set X1 and Y1. Those are the player's previous positions, which are initialized to 0 currently, but of course the player isn't at position X and Y of 0, 0, top left corner. The shoplifter's down the screen somewhere, which X and Y are already set to. So I had to set the previous X and Y, because that's actually used in the draw routine to erase the player in the old position and then draw in the new. Okay, moving on into the main game loop, lines 3000 to 3020, just fits. Okay, so you can see 3000 is being commented out and replaced with the second 3000. The original game, that's the symbol for moving the cursor to the top left corner to home, which is a common thing in basic games. Move the cursor up to the top position and then refresh the screen. And it would print 18 spaces. Those aren't blank spaces. They're actually more like cursor writes across the screen. And it's doing a mid string on the time string. So that's the clock that's running in the game, the hours and minutes. And then it prints the $sign and the score. So in the optimized version of that, you'll see I got rid of the space command because I found that just printing one constant string with the home and a bunch of cursor writes was faster. You can benchmark that in a tight little loop, run 100 or 1,000 iterations of it and time it. You can even use the TI string as I've shown in previous videos to benchmark these sort of things. The important lesson here is almost always constant strings print faster than anything else. It's just the extra time it takes for the interpreter to parse something like a space function. Printing constant strings is the fastest thing BASIC does. Okay, line 3002. It checks to see if the minute field, the middle two characters of the 6-digit time string, are 11. 11 is the closing time of the store, and you lose the game if it gets to 11 o'clock. And the program jumps ahead to line 10,000. That's the little alarm that we're at the end of the column. So that's preserved in the new one, but what I did was add the get iString. All get does is gets a character from the keyboard buffer if there is one. If there isn't, it just puts a null string in iString. And I moved that to line 3002 so that I could eliminate 3004, which was just a standalone get iString. It's always faster in Commodore BASIC to pack extra commands onto one line because there's a little bit of overhead every time the interpreter gets to the end of the line and has to find the next line of BASIC. It's just quicker to process a single colon like here, when you chain commands together on a single line. And that was just the handiest line that had some space and it didn't affect the logic. Note that you can't add extra commands after an if-then without possibly affecting the logic, because the code after the then only gets executed if the then was true. This is essentially an implied then go to. Then 1000 means then go to 1000. So even if that line is true or false, code after over here will never get executed. So you can't add the get I string to the end of that line. Okay, line 3003, I erased entirely. You can see it's remarked out here, but there is no other 3003. We've got one game over condition here if you've run out of time. Here's the other game over condition. If your score equals 13,600, then this is the winning game over. That means you've collected all the money in the game, and then it'll go to line 20,000. And what I've done is I've moved that further down to line 3170. So we'll see why I moved that score check further down. Okay, 3004 we already dealt with. 3005. This is copying the shoplifter's current X and Y position in X and Y here into X1 and Y1. And this is common in video games. You take a backup of the character's current position, you modify the X and Y positions and test, is that a valid move? In this game, can you do that without like walking into a shelf, for example, or trying to walk off the map? You take an old copy, you try to move. If it's a good move, then you allow the player to stay in the new position. If not, you restore the player's position back to those old variables. So I've done that, but I've added an extra variable here called R. And R is equal to K, which was defined earlier, but it's the screen memory minus 1, I think, 32767. That screen RAM or video RAM for the PET is K. And then you add the X position and add 40 times the Y position. What we're doing is spending some CPU cycles here to generate this R, but it's going to save us lots of cycles in the upcoming code because there's a whole bunch of close variations on this. And this 40 times Y in particular is quite expensive, and it was being done many times in the old code. So we're doing one R calculation and then just doing small plus or minus offsets to that to look up screen RAM. Really, this R is going to be used a lot for that collision detection, whether the player can move, whether the player can pick up or shoplift the dollars off the shelf or whatever. Okay, next we'll list 3010 through 3040. Okay, so this is 4 lines, really 4 lines of code, of course doubled because I've remarked out the previous version of it. This is the code that handles the 4 different directions that the shoplifter can move. So if you see the original here, if I string equals minus, well that's here. That's the same as moving the character to the right. And you can see in the original, x equals x plus 1, moving to the right. And then there's a bunch of peaks there. If peak k, that was that video RAM we were just talking about, plus x, plus 2, plus 40 times y. So it's a bunch of math to check to the right of the character. If it's not equal to 32, that is a blank space, or another peak, which is a couple characters down because the character's a few characters tall. So we're going to check out like near his head and near his foot. And if that's not 32, then we go to line 3070. That restores the position. So basically, this one line of code, this old line of code, checked. Are you pressing the key for right? If so, then move the X position and then do a bunch of math to figure out, is that a valid move or is the player walking into a shelf? And, you can't do that. So that was the old code. Okay, and before we get into this in more detail, the optimized one, we'll just go through and see that 3020, is a very similar line of code, but checks for the key 0, which in this little T cluster is trying to move to the left. And you can see x equals x minus 1. And then down on the original line 30, we check for the key 2, which is up in this cluster. Up is the same as y equals y minus 1. That's because y equals 0 is at the top. Subtract from y to move the character up the screen. It's all very common game logic. And finally, if I string equals the dot or period, then y equals y plus 1. And in each case, there's all this peeking to determine if the move is valid. And if it's invalid, then go to line 3070. Okay, so I want to look at this optimized line 310, which will be representative of what I've done to all the different lines of code. But because my optimized version actually does a lot more than just replace 3010, it actually replaces other lines of code. I'm just going to list this differently. First, I'll list 3005 to 3010. This is moving the character right, plus it's showing that R calculation I already talked about. And then I want to also list 3041 through 3080, which is some of the other logic that we replace. Okay, so to look at optimized line 3010, we're again checking if iString equals minus, character right, but then it really changes quite a bit. Instead of just making x equals x plus 1, I've done some Boolean logic here where x equals x minus, and then in brackets, x is less than 37. So what this does is it's checking, is x less than 37? If so, it's true, and this clause here equals -1. In Commodore Basic and several other Microsoft Basics, -1 is true and 0 is false. So if x is less than 37, it will return -1. Subtracting -1 is the same as adding 1. So you can see that x equals x plus 1 if x is less than 37, that is, if it's not over at the right edge of the screen, it's a 40-column screen from 0 to 39. If x is 37 or greater, this equals 0, and x won't be incremented at all. X will just stay the same. You'll be adding or subtracting 0. Okay, so why did I do that? Well, if we look down here, there's a line at 3044. After all the character movement was done in the original version, then 4 lines of code would get executed every time. We check, is y less than 6? If it is, bump y up to 6. If y is greater than 22, if x is less than 2, and basically it's like a boundary checking. It's making sure that the player does not leave a rectangular gameplay area. And there's nothing wrong with that logic, but you can see 4 if statements are being executed every time, whether or not they're valid. In our case, we're combining line 3044 into here. We're only checking if we move x to the right. Of course, the only thing we have to do is check that it's not exceeding the right boundary of that. And we're even working it in where he won't even move if he's not allowed to, all in this one line. So that is a ton of savings right there. That's a very important thing. Only check a variable that's changed. There's no reason to check a variable if it's just the same as it was last time. I mean, assuming that the initial state is okay. Okay, so 3041 through 4044 are all eliminated in the same way, one line at a time, in our revised editions of these lines. Okay, next, we still have to check if there's a shelf there. So we're going to peek, but instead of having to do all that k plus x plus 40 times y business, we've already calculated that as r, and all we have to do is check the difference. So you might notice that this is r plus 3, but the original was the equivalent of r plus 2. We've calculated r before x or y are changed. In the original code, x is being incremented here. So x is 1 larger here than it was for us when we calculated our r. So that's why there's going to be a off by 1 or off by 40 if you're going up or down discrepancy between our calculations and the originals. And you also notice that we flip this around. We're checking, is it equal to 32, while the original was checking for not equal to 32. So if it's equal to 32, that means it's a valid move. Then we can go if, and then we can check if we call this the head collision, the top right collision of the character, then this is the bottom right corner, down 80, because each row is 40 characters, so down 2 is 80 characters. In the original, all this stuff had to be evaluated, and because the original author used OR, then all this has to be evaluated, and then a logical OR is done between them to finally decide what to do. In our new way, we're doing a single peak. Only if it's positive, only if it's valid, then we bother checking the feet. Otherwise, it just drops out and it's done. So there's a lot of times you can do a very equivalent thing. If you just rethink the logic, you can make it more efficient. Yeah, did I say 32 is just the character code for a blank space? So the aisles are all full of blank spaces. I've been told that this kind of logic with the then is called short-circuiting in modern programming speak. So in the old way, if it was a failure, like if the player can't move there, then it would jump ahead to 3070. And if we look here at 3070, it used to reset the player's position based on the old X and Y, old X1 and Y1, and then go to 4000, which jumps ahead to the Warden logic. So by eliminating all this, we've kind of inverted the logic. We've managed to get rid of all this. Oh, and I forgot to say, in the old flow of the code, after the boundary checking was done, it would do this go to 3080, which then starts to print the character in the new position. But we've remarked all that out. We don't need any of those lines of code anymore. So we flipped it around. So 3070 is now reached if any of these fell through. So before the go-to was taken, if it was like a failed move, now we're doing the go-to if it's a successful move to 3080. We're jumping ahead here to where it starts to print the shoplifter. And 3070 is reached in our optimized version, just it falls through to that, and that must be a failure, in which case we set player position back to where it was. So in a sense, we've just totally inverted the logic. And there's no need to redraw the shoplifter because the shoplifter hasn't moved. So go to 3120 allows us to skip over the player redraw that was causing some of that flickering in the original version of the game. So that's an improvement as well. Okay, so I don't think there's any need to go into each of these. That was 3010. We looked at moving right in detail. 3020 here is moving left. And you see we've just flipped the logic around. We're now checking if X is greater than 2, Y 6. It's just those same gameplay boundaries. And just doing the same sort of thing, except peaking different positions depending if the player's trying to move left, up, down, or right. You're just doing slightly different math, but we're just following the example of the original with our new inverted logic. Okay, this next section, the original did all this code if x divided by 2 minus the integer of x divided by 2 is not equal to 0, then go to 3110. And I kind of puzzled over that code for a while and then realized it was just the same as if x and a Boolean logic of 1, basically and whatever the number is it even or is it odd? And if it's odd, then go to line 3110. So all this above here can be reduced down to if x and 1 will either return a 0 or a 1. And if it's not 0, then it'll be considered true, and it will branch ahead to 3110. Really, all that code does is it an odd number or an even number. And the reason it cares is because you might have noticed all the animations in this game just have 2 frames, an odd frame and an even frame. So as the player moves horizontally, he's just flipping between 2 different frames. And so you just use the X position as an input. Which animation am I going to do? Animation 0 or animation 1? Or frame 0 or frame 1? And he goes flip, 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 doop, doop, doop across the screen. He makes that sound too, just like I did. Okay, line 3100, it draws the player's head and body. Now line 3103 in the original did the same sort of calculation. All that y divided by 2, etc. is really just, is it odd or even? So I just reduced that down to if y and 1 equals 0, then we print that bracket. And if not, then we print that line. I think that's just to make his legs animate. And here's the other frame, like up here, we jumped ahead if his X position was, odd, to 3110. This just prints the player, but the other frame. I'll show it on the screen, just so if you didn't notice there's 2 frames. Okay, so once the player's done being drawn, then line 3120 is checked, and it's checking I string. That's the character input. It checks if the input is not a space. Well, the space is the steal button. So if the player doesn't try a steal, it just goes ahead to line 4000, which is the Warden logic. If the player does try a steal, then we're going to continue on from here. Okay, line 3140, all I did was get rid of this little for next loop. That's just a very brief delay as part of the animation. I'll show you. I didn't actually delete it. I just moved it, and I'll show you where I put it, just because I think it made the game feel a little bit snappier. 3150, this is checking for character 164. Well, that's a inverted $sign on the shelf. That's, is there a dollar there to steal? And if so, the original would then poke a 160. That's an inverted space. So that would erase the dollar from the shelf, and it would jump ahead to line 3170, which will give you the points for stealing that dollar or 100 yen or whatever it is. Okay, but optimized version, instead, we're just using that R still, very handy, to reduce a lot of the math. And then we can also use it for the poke. So you see how much shorter that is. It also executes a lot faster without that multiply, and go to 3170. How elegant is some of this code, eh? Where, is there a dollar there? Yes. It's deleted from the screen, and going to jump ahead to the logic for that. And line 3160 checks the other spot for where a dollar may be. It's kind of funny. It doesn't even bother to actually check which way is the player facing. It just checks 2 spots. Basically, only one of those can be true because of the distance between the dollars on the left shelf or on the right shelf. I thought that was kind of odd, but I didn't see any real savings in adding extra logic just to get rid of this logic. It's often a trade-off. Okay, and the original, it just went to 4000. Well, so you see what I've done is I've added that little I loop here, but I added it after. It just made it feel a little snappier. Before you try a steal, there's a bit of a pause. So now the pause only happens if there was no dollar to steal. So it discourages you pressing the space button, to try and steal where there isn't anything to steal. But if there is something to steal, then it just makes it a little bit snappier. So if you really don't like that, you can move it back yourself. I don't mind. And it jumps ahead. So it gives you that little penalty here, time penalty at the end, and then goes ahead to line 4000, which is the Warden. Okay, line 3170 is where we increment the score by 100. That's why I kind of think it's like roughly 100 yen to $1. So that's why I kind of think So all this code is the same. This is a little sound effect. This little J loop going by -10, that's that little whoop sound. When you grab some money successfully, it just does a little poke to this V register, which is like the audio register for this timer. It shows how easy it is to make sound effects on the PET, if your PET supports sound. But then what I did here was I added, do you remember way up at the top, I had removed the check for the score equals 13,600. This is the game 1 condition. I moved it here, and the reason for that is because this is the only place where the score goes up. When you successfully grab money, we increment the score. It doesn't happen anywhere else. So why check the score every time through the game loop if it's not incrementing? It's that same principle. Now we're only checking when necessary, although that had a little gotcha, which I'll get to in a bit. There's like a little side effect or a little bug, but I noticed it and handled it. Okay, so this is just checking. I didn't change it here. This is just the Warden walking across the screen. If he reaches the left edge or the right edge, then we limit him and reverse his direction. Q equals 0 means move left, and Q equals 1 means move right, I think. But you see here, I've commented out lines 4005 and 4010. It was doing a weird thing. It would check for a random number, and if the current Warden horizontal position, that is A, is equal to a random number from, well, that valid range of his positions, if you roll a random number and it happens to equal his current horizontal position, then, well, this is the weird thing. He won't change direction. He'll be forced to move right, or he'll be forced to move left. But if he was already moving left, then what is the point? Like, that's like you do all this randomness, and then only 50% of the time it matters, because you might just tell him to go in the direction he's already going. So that didn't really make sense to me. So what I did was get rid of the first line and just consolidated it into one line. If his current position is rolled, then randomly send him left or right. I think that's functionally equivalent. Like before, there are 2 chances each game loop, but one of them would be guaranteed to have no effect. And now there's only 1 chance per game loop, but it has a 50% chance of no effect. Is that the same? I don't know. I guess I need a statistician or somebody who understands odds. Is that equivalent? What I was wanting to do is get rid of doing this multiply by 35 twice for no apparent reason. So that's why I've done it here. If I'm wrong, let me know. Okay, so now I'm going to list from 4050 to 4090. So the original would do another one of these kind of odd or even things. It's the Warden's current X position or horizontal position A, divide it by 2, and subtract the integer of A divided by 2. Again, this is just basically doing a modulus of 2, returning either 0 or 1 in A1. So I replaced that part in here, A and 1, just like I did before. But I've also added in this whole on Q times 2 plus AM1 and then go to. So I'll have to explain that. And I added this 4055 here. Oh, I didn't comment that I added that, but I did. Okay, so here in 4060, this is the original. What it would do is it would take the Q, that is the Warden's current direction, and of A1, which is that modulus on his current horizontal position, and then if both were true, if he's moving a certain direction and his current position is odd, then it would print this particular frame of the Warden. Then it would increment his position, A equals A plus 1, and that would go to 4095. That's just below this screen full. And you can see here on 4060, 4070 is the same, except it's if Q equals 1 and A1 is 0, rather than up here not 0. I guess this is one time where it would be nice that I didn't have the two versions merged together, but well, anyway, we'll want to see my optimized versions in a bit. So basically, there are 4 possibilities here for drawing the Warden. There's 2 frames of him running to the right, and there's 2 frames of him running to the left. All this logic, A and Q, are combined into 4 different states to choose. Do I want to draw him right? Do I want to draw him left? Do I want to draw his first or his second frame of animation in each of those directions? So what I've done, so that's, for example, let's look at this one, 4060 that we commented out. Basically, I got rid of all this if and then, and we can go straight to just doing the print of the Warden, incrementing his A, and go to 4095. So it's very similar to the old logic, except we got rid of all this preamble. And remember that if this preamble is false, then 4070 is run, and it has to do all this calculation again, and 4080, and 4090. So potentially, depending on which direction he's going, it's like the speed of him will change a little. It has to do as many as 4 cases to find the true one. So my new line 4050 gets rid of that by multiplying Q by 2. So this will be either 0 or 2, and then adding that A and 1. So it's basically combine Q and A into 4 possibilities, the numbers 0, 1, 2, or 3. And on go to, we'll take the number 1 and go to 4080. If it's 2, it'll go to 4070. If it's 3, it'll go to 4060. And if it was 0, which is the other possibility here, it will actually not go to any of those, and it'll fall through to 4055. So you notice that 4090 is missing from my list up here. 4090 is one of the lines. And that's because I've duplicated 4090 to 4055. Case 0 falls through to here, and cases 1, 2, and 3 are handled here. It chooses between those 4 different states in roughly the same amount of time. So I think that that's not the hugest improvement, but maybe that's kind of useful for handling. If you're a C programmer, on goto is very much like a switch statement to handle different cases. And it really is one of the most powerful constructs in Commodore BASIC, the on goto, or on go sub for that matter. If people are programming those 10-line BASIC games, this is an amazingly useful construct. Okay, and we'll list from 4095 to 5045. Okay, so this line 4095 here, this code here compares the Warden's X position to the player's, and then does a couple peaks, and all that's doing is checking for a blank aisle, I guess, below the Warden, and therefore whether he has line of sight to the player. He doesn't have to check the whole line because of, again, the geometry of the level means that as long as there's no shelf right below the Warden, he can see all the way down the aisle. It must be an aisle all the way down. So it's kind of funny that just that single bit of code here does the detection. That is the stealth part of the game. Does the Warden spot the player? It's just one line of code. Kind of amazing. And if he does, then it jumps to line 5000, and that's the animation where the Warden tracks down and drags away the shoplifter. And the only improvement I made there was making that short-circuiting. Instead of doing a bunch of ands where each one has to be evaluated, I'm just doing a then if and a then if, so that it aborts as soon as there's one false instead of combining them all logically. And that is it. Line 4200, that's the end of the main loop. It goes back up to line 3000 and repeats. Okay, I think we're on to the very final block here. So I've actually replaced line 20,000. I'm finally breaking my pattern. And this is the original one that I've remarked out. And I've copied it down to line 20,002 because I really needed a line 20,000 because there's some lines that go to this line. I didn't want to change all those go-to references. So I just wanted to change it in one place. So this line 20,000, that's a copy of line 3,000 way back at the beginning, which prints out the current time and the score here. Okay, so as for why I did this, so I don't feel too good about duplicating a line like that. Seems kind of wasteful, but at least I did clear a whole bunch of other lines. But this was necessary, or at least this was my solution, because of a fairly subtle bug I noticed. When I optimized line 3170, which is where your score gets added when you successfully steal, and we check for the game over condition, well, when that's true, it immediately jumps to this line, 20,000, that you won the game. But previously, when you would steal, there was no check for the score. The game loop would finish. It would go back up to line 3000. The time and score would be updated at the top of the screen. And then the check would happen for whether you won the game. And it would go to 20,000. So my optimization saved time, but introduced the bug that the score is never updated on the screen. Your score variable is updated, but it doesn't get displayed on the screen because it jumps right to the end. So basically you would win the game, but it would say 13,500 instead of $600 on the screen, or yen or whatever. So I only noticed that I beat the game and noticed, hey, that number's not right. And that's why. So this often happens when you optimize something, you can interrupt the flow of the game logic, and it can have consequences that you have to check for. Optimizations aren't always free. There's probably other ways of fixing it, but they all have some cost. I guess I could have just reverted the optimization as well and given up on that particular one. That's an option too, but I want to keep with it. So my solution is just to duplicate the display line. Of course, if it was a subroutine, then we could go sub it, and it could be just the same line of code, but go sub and return have overhead to them as well. So then, just to save these bytes here at the end of the game, when you win, every game loop would have an extra go sub added. So there's always trade-offs, right? Wait, I just want to point out, for example, next k comma j. It's equivalent to just going next, next. You can name the variable names. This is actually quicker, next, next. But I didn't optimize that because this is part of a sound effect here. Here are these j and k loops. Poke v comma k, that's making some sort of whoop 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 sound. Well, there's no point optimizing that, because by optimizing a sound effect routine, it's time sensitive. I would actually be affecting, if I made it faster or slower, it would affect the sound of that sound effect, or at least the speed of it. That's probably not a big deal, but don't just blindly optimize, because sometimes that will affect the game in a negative way, or at least take away from the author's intent of having the sound effects sound a certain way. I mean, maybe all my optimizations are taking away from the author's intent. He wanted the game to be a little on the slow side. I don't know. I don't think so. Anyway, the original game is there. You can play it if you want. Okay, so that is the walkthrough on the PET. Oh, that took a long time. Let's go take a look at the C64 and Faster 64 and just figure out how we came up with that line 10, that dimension line of the variables that was part of the optimization. Okay, I've got that Manbiki D64 that I've added a couple files to. Here's Faster 64. We'll start that up. And I'm going to load up Shoplifting Boy, and we'll load up the cursor control version. Oh, out of memory error, you have to type new after you start Faster 64. We'll load Shoplifting Boy. Okay, and we'll list it. And I just want to point this out. this is a problem here. 2564. If you remember, our line 10 had that dimension, and that worked fine on the PET. When I load that on a Commodore 64, it displays this garbage line number here instead. 2564. So I want to give a shout out to my patron, James Pohl, who sent me a message about this. He was playing around with Manbiki Shounen, working on the C64, and he found the first line was getting corrupted too. So actually I had seen that, but I just kind of ignored it because I get in so many, when I'm doing any of these projects, there are always these bunny trails to follow. But I get so few videos done compared to what I'd like to do because I'm always following every one of these. And I investigate it, and honestly, sometimes I'm bored of the idea by the time I finally figure it out, and I try, well, where was I? And it's like when I'm doing Commodore stuff or any of my 8-bit stuff, I have tons of fun, but it's like a stack where I discover something and I follow it and I follow it. I can't even remember where I was at the beginning. I lose interest. I keep following whatever's interesting and the video doesn't get made. This was interesting. Why does it say 2564 there? But I deliberately ignored it. And then James sent me a message and I thought, I better check this out. So I did. Oh, okay. So all that to say, we figured it out. But I'm not going to explain it now because it's a whole video of its own. All I'm going to say is to work around it. Let's try this 2564. And let's try listing. There, now it's gone. We fixed it. And line 10 was a dim or whatever, but you know what? We're not even going to do that. Maybe I'll put a rem there. So all we're trying to do right now is we've got Faster 64 started, and we're trying to get this PET game working on the C64. Number one was to fix that corruption at the beginning of the program. We've done that now. Number two is this is screen memory on the PET. It's one less than 8,000 hex. So we're just going to put it to 1023, one less than 0400 hex, which is screen memory by default on the C64. And we can actually ignore all these. 59464 is E848 in hex. Well, that's part of the kernel ROM. You can poke there to your heart's content and it won't cause any problems. Not in the default setup anyway. So we can ignore all those extra pokes. Like here to V, that's the, those are the volume or the audio register. It doesn't matter. We'll just ignore them. Okay, so what we've done here, just by fixing that one thing and changing the screen memory variable, is we've made a Commodore 64 port of this PET game. Not a good one, but it should work. Okay, now we're going to run the game. And we're going to play pocketing something from a store. And we're going to start it up. Oh yeah, that one character, the pound character, is different. That is like a backslash on the PET. Okay, so we're just going to start the game here now that we've poured it. And, ooh. Okay, so I'm going to stop. I'm going to type end. And there, all the variables printed out. Look at this output. So basically we ran Faster 64, and now it's dumped out all the variables. The line I ended up with in the PET game, the line 10 was dim A, comma, I string, comma, X, comma, Y, R, X1, Y1, S, K, V. Well, here, I'll just put that in. So if we go here, you'll notice J is the highest variable, then there's I, and then there's K, and then there's A. So why didn't I use these? Well, J and I are variables that are used by all those internal loops for the animations and for the sound effects. And as we discussed earlier, there's no point optimizing for sound effects or delay loops because, like, what's the point in speeding those up? If you wanted them to be faster, you could just actually change those loops so that they don't count up as high, for example, for a delay loop for an animation. You could just go in there and tweak it yourself. Don't waste one of your fast variables, that is the variables at the beginning of your dimension list here, on something that's just a loop, burning cycles essentially. Okay, so that's true for J, I, and actually K is a funny variable. It's used a couple different ways in this program, sometimes for legitimate gameplay purposes and sometimes for a loop. So I actually demoted it. I still have it in my list, but I put it way down here near the bottom. Did I mention, okay, so Faster64, if you didn't watch the previous video, every time there's a variable access, it just keeps a list of the variable name and how many times, every time it's accessed, it gets incremented by 1. So that's what this is doing here. And then it sorts it. So this is why it's very useful for making this dimension list. So the first one that I consider valid is here at A, had 900 accesses. That's the shopkeeper's position. And that gets used every single frame of the game, or every single game loop. Okay, I ignored CO. I gotta be honest, I don't even remember what CO was. We'll try and find that in a moment. Okay, the next one though is I string. That's the keyboard input. Every time you press a key, well, that's accessed once anyway per game loop, even if you don't press a key, and more if you actually do move. V is that sound effect volume register, but that one I also didn't consider very important, so I put it down near the bottom of the list here. And now we're getting into some more. Yeah, X is the player's position. Not sure about in string. Here, I'm going to keep notes. Okay, we'll find those ones after, and I'll let you know why I didn't include them. Yeah, I'm not as prepared for this last section here. Okay, and here's the player's Y position, which I consider to be the fourth most important one. Now, you see, the numbers can vary widely, X and Y. It all depends which way you move. If the player simply just moves left and right all the time, there's going to be a lot more X axes than Y. I don't know, you might actually think maybe Y should go before X. Maybe it's more important that moving vertically is a higher priority. That's kind of a judgment call. TI string has a whole bunch of accesses, but the funny thing is there's no point optimizing that because that's a system variable. Actually, you might not even be able to dimension that. I don't know. Oh, I'm worried about crashing it. I don't want to. That's something for another time to test. Can you even dimension TI string? H string is one of these reserved variables that's right at the beginning of the program. It's a string constant. It's got a relatively low count. Maybe it would be worth defining that. That clears a horizontal line on the screen. X1 and Y1 are the backup values. So you see I've included them here. It's really hit and miss. Some of these, they have very similar numbers of accesses. So it's just sort of a judgment call. But at least it gives you some empirical data. Now remember, different runs of this program could end up having some pretty different values. So if you're taking this really seriously, you might want to do a whole bunch of runs of the program. Okay, and then other ones, S, well, these are just some other variables. I4, I3, yeah, those really had very insignificant amounts of use. Okay, so let's try and find where are these COs. Well, I see CO. That's like a counter. Okay, so we ran that intro again. If I list, no, I'm going to type end. So it was CO and IN string. If we list from line 900 and on, we'll see here, basically this is the loop right here that checks during the title screen. It gives the player a chance to press S to start right here. And it's using this IN string as a get. So this is just like iString, the main game, except it's checking for you to press S to start. CO is just a count. It gives 50 loops, 50 times through the loop for you to press S, and otherwise the demo mode, the attract mode, continues on. Okay, so that's why I excluded iString and CO, because they're just used in the title screen. No sense optimizing that. Okay, so that's how I came up with that final dimension line for line 10. As you see, it's not a science, an absolute science. It's a bit of an art, but you gather data and you make the best call you can. It's a neat little tool, though. Okay, that was a monster episode. Okay, that's it for today. Thanks very much to my patrons for their support. Thank you to Ryan again for bringing up this game. Thanks very much to Hiroshi Suzuki again for making this original game. Thank you for watching, and we'll talk to you next time.
Hey, stop right there. What's that supposed to mean? Can't you say anything else? Well, what else? Positive or negative? 0 or 1? True or false? On or off? You're a bit where's your program? Am I your program? Oh, great. Another mouth to feed. You're a bit, and